First of all, it's a pleasure to speak in this workshop in the Simons Institute. And I will talk about a joint work with Andrea Montanari, one of the organizers, and Subabrata Sen, who is also here, who is a student advised by us at Stanford University. And I will talk about extremal cuts of sparse random graphs. And it's an example of a problem which is where some interesting developments which are very useful in theoretical computer science and discrete mathematics can be gained by following intuition from statistical physics using probability theory as a bridge to provide the proofs that connects the two. So first let's talk about what the question is. So we have a graph, a collection of vertices. Here is a graph, a collection of vertices, the blue dots, and some edges between them. And we define a cut. A cut is simply a way to divide the set of vertices into two parts. Let's say S and V minus S. And let me assign +1 to the vertices in S. Here there will be 1, 2, 3, 4, 5 vertices in S, and 7 vertices in the complement of S, which is on the other side of my cut, which is the red line. And this cut produces a cut set or a cut width, and that's a number of edges that are simply cut by the cut. Like visually here, it's exactly 2. So it's a number of edges connecting S to the complement of S. And you can observe that one way to count the width of the cut is to do the following. We will label the vertices in one side by +1, the vertices in the other side by -1, and we multiply the indices, we multiply sigma I by sigma j across each edge. Then if we are on the same side of the cut, the product will be 1. If we cross the cut, the product will be -1. So if we take twice the size of the cut minus a number of edges, we will get 2, right? We will get 2 minus 1. So 1 here and -1 in everybody else. And that's exactly going to be the same as a Hamiltonian for the antiferromagnetic easing model on the graph G. And that's a connection between the problem in computer science, find extreme cuts, and the problem in the statistical physics intuition, study the antiferromagnetic easing model on the same graph. But we will talk about it in a minute. So for the time being, let us define 3 different extremal cuts that may be of interest to us. The first one is a minimum bisection. We are trying to minimize the width of the cut, but subject to the constraint that the set that we cut is balanced. We take exactly 1/2 of the vertices on one side and 1/2 of the vertices on the other side. Let's say we assume from the beginning that our graph has an even number of vertices, otherwise we round it a little bit. The point, of course, is that if you don't have this constraint, then one way to minimize the cut is simply to take one vertex on one side and everybody else on the other side, which seems kind of unfair. The other extreme is a maximum bisection, exactly the same, but now if before we try to put as many edges as possible in between the group, between each group, now we try to put as many vertices and as many edges on the cut and as little vertices between the group, little edges between the group. Or alternatively, we can look at the maximum cut, max cut, where we have no constraint, but we are trying to put the maximum number of edges in between. When we try to put the maximum number of edges in between, you see there is no benefit in taking one to be single and the other one to be all of them. So there will be 3 extreme cuts that we will want to study, and they are very closely related to each other. So this problem is interesting in computer science and discrete probability, discrete mathematics, and also in statistics for many reasons. It can be used to cluster similarity matrices. It is a good tool often to study graph layout, which is optimizing a certain labeling of the vertex of the graph. So we can use extreme cuts as a way to choose optimal labeling. This is related from theoretical point of view to isoperimetric number. It can be used as a suboptimal algorithm for detecting community structure in social network. And this can be done with connected to this problem. And there are many more examples. So instead of talking about the examples or the applications, let me focus on the theory. And what is known is that the complexity of these problems is difficult. These are all NP-hard problems. So trying to find the minimum bisection, maximum bisection of max cut for a general graph of degree of number of vertices n is an NP-hard problem. So finding a good algorithm in the worst case is kind of hopeless unless you believe that NP equal to P. It is even hard to approximate, but it is hard to approximate only if you insist on a very good approximation. That is, if you want to approximate up to within a factor little order of 1 the value of this bisection, then the problem is known to be hard. There is actually a semi-definite programming algorithm due to Gremens et al., which does the work up to a factor 0.878, but there is a proof a few years later given by Trevisan et al. That it's hard to do it once you want a factor bigger than 16/17. So, and the same will apply for, this is for max cut, I think, and the same will apply for minimum bisection. However, as we will see, it is trivial to approximate within a factor of 2, for example. I will show you in a minute. So there is a very rich theory related to the problem, to NP hardness, and also to best approximation of this problem. But we would like to do something else, which is not to focus on the worst case, but actually to talk about typical complexity, that is to study the average behavior. If we just choose a graph at random. So if we choose a graph at random, we need to decide what random graph models we want to work on. And there are two classical models that we may study. So the first one, the most natural one, will be the Erdős-Renyi random graph. In this case, we have n vertices, and we either choose edges independently with some probability p, or we choose our graph uniformly among all the graphs having a fixed number of edges, which is given by the expected of what we will take otherwise. These two models are canonically equivalent, and the average degree, which characterizes how dense a graph is going to be, of course, n times p. Right? We have n vertices, each one may have up to n edges, each one is chosen independently with probability p, so the graph G and P correspond to average degree gamma. We can do another model, which is more restricted, is a random regular graph. Here, instead of specifying the average degree and choosing the vertices at random, the edges at random, here we specify to have a uniform graph, but we insist on the degree of every vertex to be exactly equal to gamma. And these two models are not the same, but they are comparable if you choose gamma or P to be gamma over n. And the sparse graphs correspond to the case where gamma stays order 1. So the degree of the vertices stay of order 1 while the graph grows, as opposed to the dense case where the probability stays constant and the number of edges grows quadratically with the size of the graph. So we will be interested in sparse graphs of one of these two models, either the Erdős-Renyi or the random regular graph. Okay, so extremal cuts of random graphs in this situation has a long history, starting with the work of Bolovash from 1988 and a series of works. And they study various ensembles. Some study the regular graph, some study the Erdős-Renyi graph, some study the mean bisection, the max cut, the max bisection, against the max cut, and against the max bisection. And they provide different bounds. Generally, concentration bound correspond to something that we cannot do better. We can calculate the average value, and if we have control on the concentration, then we know how large or how small the maximum can be. So concentration bound gives us bound for one direction of what cannot be done. Algorithmic bounds is providing some other way to get something done, right? Not just a mean, but some fluctuation. And of course, if you try to make them close to each other, you can maybe get the answer of the asymptotic behavior. Some work, like Bolovash and Alon work, correspond to the large gamma case. And some work, like the work of Coppersmith et al. And Dowd et al., correspond to the small gamma case, where in Erdos-Renyi case and Max-Cut, there is a transition that happens at gamma equal to 0.5. In the Erdos-Renyi case, you can even lower the average degree below 1, because you just make p smaller than 1 over n. And in this case, there is a phase transition at gamma equal to 0.5. In the Max-Cut, you can actually make almost all the edges be in your cut. The error between the number of edges and the size of the cut is little order of n. Once you cross this threshold, the error suddenly becomes order of n. This is not present in the regular case, because in the regular case you don't start with such a low graph. Okay, so what is a typical result coming from this long history in the study of discrete mathematics and combinatorics? The typical result is that if you take a graph, for example, from Erdos-Renyi with parameter gamma over n, or average degree gamma, or you can take the regular case, then with high probability, the max bisection, and you can do the same for the mean bisection of the Max-Cut, will be around n gamma over 4. I will explain where this comes from. And the next correction term will be n times square root of gamma, and bounded below and above by 2 constants. In a max bisection, the constant will be positive. In the mean bisection, the constant will be negative, because you are going below. And in the Max-Cut will be similar. And many of these works of Bolovash, Alon, and Gamarnik et Lee are working around the question of improving the constants C1 and C2 with the hope of getting them as close to each other as possible and nailing down the correction term. Okay, so let me explain a little bit what is a concentration bound, the classical argument. How do we get a basic bound? So here is an example. We take n equal to n number of vertices. E is n gamma over 2. Let's fix a particular bisection. So we just fix a particular set of vertices of size n over 2 and decide to study what is the size of this particular cut. Our graph is random, so even if we can fix the cut first and then decide on the graph. Why not? If we do that, each edge is going to appear in our cut with probability 1/2. If it is an edge between S and the complement of S, it will appear. If not, it will not appear. So the expected value of the cut width for this particular choice of S is simply going to be the number of edges divided by 2, or n gamma over 4. And from this you can also see that you can easily get an approximation up to factor 0.5 for the Max-Cut, because the maximum value of the Max-Cut is the number of edges. And you can see that simply choosing randomly a cut, a bisection, gives you already a value, expected value of the cut, which is E over 2. So if you try 7, 8, 9 times, with high probability you will get yourself at least E over 2, which is at least half the size of the Max-Cut. So this is a trivial bound, but you cannot go all the way to size 1, this method. Now, you can also use the Zuma-Hoeffding argument, because if you have an Erdos-Renyi graph, and what Bolovash did is a slightly more involved argument for the regular graph, but for the Erdos-Renyi graph it's really easy, because all the edges appear with probability p, so the size of the cut minus the expected value of the size of the cut are actually quite concentrated. So you can conclude that the probability that the cut will exceed its expected value, when you choose a cut of this size n over 2, exceed by delta, you can get an exponential bound for this result. And then you can do a union bound. Suppose you want to exceed by delta times n square root of gamma, then you plug here the capital delta to be delta n square root of gamma, and you will get the gamma will cancel, the n will cancel, and you will get yourself e to the minus n delta square over 2. This is for one particular cut. If you want to go over all possible cuts, you can use a union bound. There are only at most 2 to the n cuts because you just need to decide each vertex where it is standing. And so you get the power 2 to the n. And if you play with the delta here large enough, the negative exponent will kill the factor of the union bound and you will be in good shape. And this will give you a bound on the number delta. This is a concentration bound that I mentioned earlier on. Okay, so the end result of this bound is that the value of the mean bisection and the value of the max bisection deviate from the mean, which is n gamma over 2, by n times square root of gamma, up to constants which are positive or negative. If you want to tighten it, then you need to get algorithmic bounds that will give you an upper bound on the mean bisection or a lower bound on the max bisection, which will be better than these trivial bounds. But the moral of this story is that the term n gamma over 4 is really trivial. It's just the expected value if you choose your cut at random. It does not say anything really of any meaning about the optimization problem. So it's just, we just want to get rid of it. It's not interesting. The interesting term is the rest. Okay, so how do we move to the rest and how do we connect to statistical physics? So in order to do that, let us remind ourselves of the Ising Hamiltonian. The Ising Hamiltonian for a general graph goes as follows. You label the vertices of the graph by plus or minus 1. So every vertex has a label. So the vector sigma will be living in minus 1 to the plus 1 to the n. And you compute this term. You sum sigma I, sigma j over the edges, and you normalize by 1 over the square root of the average degree, for reasons that will become clear in a minute. Okay, so this is a Ising Hamiltonian. Let us see what happens to the max cut problem. Remember, the max cut problem, we try to maximize the sum over the edges, but we want to take only the edges that participate in our cut. How do we do it? We take 1 minus sigma I, sigma j over 2. So if we are in the same part of the graph, then sigma I, sigma j will be 1. 1 minus 1 will be 0. We are not going to count it. If we are between the two, sigma I, sigma j is minus 1, and this will count as 1. So this is just a complicated way to count the max cut of a graph. But thanks to this way, we can separate the 1/2. This just gives us E over 1/2, minus 1/2 the minimum of the sum sigma I, sigma j over ij in E. And this we can rearrange again in the case that we are talking about of the average degree is gamma, so the size, number of edges is going to be n gamma over 2. And our cut, I remind you, is a set where sigma I is plus 1. So the first term will be the n gamma over 4, that's just half the edges. And the remaining term will be square root gamma over 4 times the minimum of the Ising Hamiltonian. So the coefficient of square root of gamma is given by the minimum of the Ising Hamiltonian. So in particular, if we want to do a bisection corresponding to S having a size n over 2, that corresponds to us thinking about omega n, the set of all vectors of plus minus 1s, which are balanced. The sum of all sigma I equal to 0 is the same as saying that we want exactly n over 2 to have the value 1. Right? N over 2 will have the value 1, n over 2 will have the value minus 1, sum them all up, you get the value 0. So the max bisection and the mean bisection, their value will be n gamma over 4 minus square root of gamma over 4, either the mean or the max of the Ising Hamiltonian over balanced configuration. So you can see that if we know the answer, the asymptotic answer to the mean and max of the Ising Hamiltonian over balanced configuration, then we figured out the next correction term that we were after in the optimization problem. So that's a connection to statistical physics. Now, in statistical physics, usually you don't look directly at the minimum or the maximum, but instead you look at a soft or smooth option, similar to what Shurav did, or Nike did, or Andrea did in earlier works, in earlier talks. And so what you do, here is your Hamiltonian, and you create a new measure where you put a weight e to the beta times the Hamiltonian, and you divide by the partition function, which is simply a normalizing constant, to make sure that this becomes a probability measure. it is going to be a ferromagnetic Ising measure if beta is positive, so you try to make them all coherent, go together, and it is antiferromagnetic if beta is negative, so you try to make them all going in the opposite direction. What we are after is what is called ground state energy. That is, suppose you take this partition function, you take the log, and you divide by beta. If you send beta to either plus or minus infinity, the effect is to maximize or minimize the importance of the maximum or the minimum, and you will arrive to the maximum and the minimum over all configurations. That is what we need in order to study the minimum bisection or the maximum bisection. So study of minimum and maximum bisection correspond to studying the ground state energy in the Ising measure, one of them in the antiferromagnetic and one of them in the ferromagnetic case. But in both cases, we are working over balanced configurations. Right? So our partition function, our configuration space is not all plus minus 1 to the n, but only all the balanced configurations. Okay, so thanks to this connection, which is old connection with statistical physics, which was known way, I don't know way till when, but certainly 86 or before. So there are many conjectures coming from statistical physics related to the general idea that many problems on sparse random graphs, many computational problems, are connected to or can get insight by solving corresponding problem in statistical physics. Specifically, the conjecture that will be of interest to us is a conjecture from 2010 of Zdeborova and Bocher. And what they said is take a regular graph, take the uniform regular graph of fixed degree gamma, which can be depending on n and can be just fixed degree, and large n. Then with high probability, you have this marvelous identity, which says that the max cut up to little order of n is the same as the max bisection. This is not so surprising, but the max bisection is the same as the mean bisection on the other side of E. So if you add max bisection and mean bisection should be, as we know, be around the size of E over 2 plus some error. The claim is that the error is completely symmetric. The problem is not symmetric, but somehow the claim is that this is symmetric in the regular graph, and it is supported by very convincing numerical simulations. You just need to look at this very relatively short paper and at the numerical simulation, and you will agree that this is practically a theorem. It's numerically practically a theorem. But, you know, being mathematicians, we usually do not accept this overwhelming evidence and try to prove this theorem. So what you can do is try to solve this problem. I will continue not solving this problem, and you can try to solve this problem and tell you if you succeed at the end of the lecture. Okay, so before we do that, maybe a beginner step will be just to conclude or to verify that if we take the value of these problems and we divide by n, we will actually have a limit. You know, not even commit on the limit, just say that there is a limit. That might be useful attempt for mathematicians. And indeed, in 2009, a paper of Bayati, Gamarnik, and Tetali very nicely proved that for Erdos-Renyi graph or for the regular or for gamma regular graph, with high probability, the max cut will have a limit. That is, the lim inf 1 over n, the value, equal to the lim sup 1 over n, the value. And the method that they employed is using subadditivity, which means that there is no limit value provided. Right? So it's a method that says that there is a limit without ever committing to the value of the limit. And the idea that of Bayati et al. Is that they were using the same idea of interpolation as done by Franz and Leoni and Toninelli before, on problems more in statistical physics flavor, and extended it to many problems of interest in computer science, in particular the max cut, and also to the regular case, which involve harder work, because in the independent case, the subadditive approach usually looks at graph of size n and a graph of size 2n and tries to connect them. In the Erdős-Rényi, it is much easier because everything is independent of everything else. In the regular case, it requires some cutting and splicing and reconnecting without losing too much. So there is a little bit of gymnastics required in the regular case, which makes the paper quite highly non-trivial. So now we know that there is a limit, but we still want to know something about this limit. So here is a new result, and the new result in this paper with Andrea and Subabrata, which is posted on the archive, says that if you take the two graph ensembles, the regular and the Erdős-Rényi graph, if you divide all these values by 1 over n and study the behavior when n is very large, you get the trivial term, and then we get the next term, the term that multiplies square root of gamma, and it has the same coefficient. The conjecture of Lenka and Stefan Bocher is really more or less that up to little order of n, all of them have the same limit. Now, we are not as brave or as clever as to prove this conjecture, but we prove at least that the first non-trivial term is the same. So it's a one step. It's now a small mathematical evidence of an overwhelmingly numerical evidence that was before already. So what is a term? This is this term P star that I will describe in a minute, but before we do that, let me tell you what is the conclusion of this result. One conclusion is that if you know where this P star comes from, there is no more need to chase with combinatorial methods the number C1 and C2, because they will eventually, after a lot of work, converge to this number P star. So there is no need to do that anymore. The other thing that you can learn from this theorem is, first of all, the square root of gamma term has a well-defined coefficient. The coefficient has an explicit formula, and I write here explicit with a quotation mark because I wouldn't like to be in charge of finding this number, but physicists are very good at that, and numerically they found this number P star. This number P star is also the same for the three problems and the two graph models. So in this respect, it's a partial confirmation of the conjectures I mentioned above. It's a partial confirmation because it's only relevant when we send gamma to infinity. Because if we don't send gamma to infinity, the fact that the first coefficient times square root of gamma is the same does not really mean anything about the function. Because if gamma is 2, maybe it's P star times square root of 2 plus 1,000,000 or 500,000 times something else in gamma. Okay, so what is this P star? Well, this P star is related to the Sherrington-Kirkpatrick model of statistical physics. So here is the story. We take now the Gaussian orthogonal ensemble random matrix. So this is a collection J of size n by n. J is going to be equal to J transpose. It's a symmetric matrix. And the entries of diagonal entries are normal variables of 0 mean and variance 1 over n, and the on-diagonal elements are scaled appropriately, and all the elements up to the symmetry conditions are declared to be independent. This is called the Gaussian orthogonal ensemble, which has a very nice properties, a spectrum, and so on. The Sherrington-Kirkpatrick spin glass model corresponds to looking at the measure mu beta of sigma. Sigma is a vector on the hypercube, plus and minus 1, but the coefficients of the quadratic form are this matrix J. So you fix the matrix J randomly, and given the random matrix J, you compute the 1/2 the sum of sigma I, Ji, sigma J over all i's and j. This is called the Sherrington-Kirkpatrick model. And finally, here is the answer for P star. So P star is going to be the expected ground state of the Sherrington-Kirkpatrick model, normalized by n to make it order 1, and taking the limit when n goes to infinity. And at this point, you may feel a little bit cheated, because I converted one thing that you didn't know with another thing that you didn't know, and the value of this conversion is not really clear to you. Now, well, first of all, I can say that one value of this conversion is the fact that two graph models and 3 problems had the same coefficient. But even more, I can say that other people already being able to compute or predict or find a formula for P star. So what is P star? First of all, the limit exists. This limit actually does exist. This is a consequence of the Guerra-Toninelli or Guerra interpolation technique, and it is given by Parisi's formula, and this is a famous result of Talleyrand. And Parisi formula is a very nice explicit formula involving a nonlinear PD and optimization. I would not recommend to anybody to do it, but it is a formula, and you can use it to numerically compute the numbers. Now, two things that you learn from this at this point already, without worrying about the proof, is one, you learn that it is clear why, since 1988, people who used combinatorial methods were unsuccessful in nailing down the constant. Because if the constant it comes from Parisi's formula, and if your combinatorial method never sees any SK model, there is no real reason why it will ever get you the right number. So let's explain why standard combinatorial methods were unsuccessful, and I can claim with some degree of confidence still will be unsuccessful, unless they hide inside somehow the SK model. Secondly, the Parisi formula comes with a certain prediction, and this prediction explains that the set of near extremal cuts is predicted to have the full RSB structure. That is to say, finding a nearly extremal cut is going to be a hell of a difficult problem algorithmically. Okay? Well, this may explain part of the complexity, and it also means that the study of this problem, or the space of solutions, is going to be much worse than the problem that was recently tackled very successfully mathematically by Allen and Nike and their collaborators, which was focused on solving the one RSB in a under reasonably good assumptions. So here it's not 1 but infinity, and you are not in reasonably good assumptions. So this is going to be very difficult problem. Okay, so let me use the last 10 minutes to talk about the proof strategy. And what is a proof strategy? So first you prove it for mean bisection and max bisection in the graph which is independent. So you take yourself 2 advances. 1, the size of the cut is fixed. 2, which is even better, the graph consists of a lot of independent things. So first you are going to solve this, and solving this breaks into 3 steps: concentration, interpolation, and a smooth maximization. Step number 2, you extend from the Erdos-Renyi graph to the regular graph. The idea is to couple the 2 graphs in such a way that the difference is not too big. There is a tricky problem that if you simply couple the 2 graphs, the difference between the edge set of the 2 is approximately n times square root of gamma, or much bigger than n times square root of gamma. So it is not trivial, because you cannot just say, well, I will just do the calculation on one graph, and the difference between the graphs is small. The difference between the graphs is actually big, but most of the difference between the graph goes into a constant that's cancel another constant, and nothing else is left. So that's why it is a little bit tricky, and since it's tricky, I'm not going to talk about it. And the third part is to prove that the max bisection and the max cut are approximately the same. And here it's a little bit, some part is easy. It is clear that if you take a cut which is totally unbalanced, then you lose so much in the mean that you can no longer recover it with a fluctuation, with the entropy of unbalanced cuts. But you need to, the tricky part is to deal with things which are too close to be balanced. Again, it's a tricky technical part. I will skip it too. So instead, what I will do, I will just talk about the proof of the mean bisection and the 3 main steps: concentration, interpolation, and smooth max, and not worry about the other steps in this paper. Okay, so let's remember what we need to do. We want to calculate the behavior of mean bisection for Erdos-Renyi graph. It's supposed to be leading order n gamma over 4 minus square root of gamma over 4, the maximum over balanced configuration of the Ising Hamiltonian. By concentration, we don't need to deal with this object. We don't need to deal with this object. We can just deal with the expected value. The fluctuation from the expected value is going to be little order of n. So we can just worry about the expected value. And we also don't worry about anything which is smaller than square root of gamma. So our goal is to prove that 1 over n, the expected value of the maximum of the overbalanced configuration of antiferromagnetic Ising, is going to be P star plus things which are small when gamma is large and things which are small when n is large. Now we already know that if we replace the Ising Hamiltonian with the SK Hamiltonian, then we get the kind of right result, because that was a definition of P star. So what we want to do, we want to do an interpolation, or a smart path, or a Lindenberg method. We want to move from this Hamiltonian to this Hamiltonian without causing too much of an error. If we can do that, we are done, because this computation here was done by others. It's a usual mathematician's way to get to the moon. You first take a rocket of somebody else almost to the moon, and then you jump the last step. So that's what we do here. Okay, so interpolation requires 2 steps. First step is to go from Hg to HSK, and the second step is get rid of the balanced configuration. Right? Because we work only on the balanced configurations, and in the last step we need to take the SK model on balanced configuration and move to the SK model not on balanced configuration. I will not talk about the second step, I will focus on the first step. How to go from the sparse graph to the complete graph. So what you do, you want to construct a path. What does construct a path means? A way to change slowly from one side to the other side. You don't want to do a radical change, you want to do a slow change. And the strategy is to take a Hamiltonian which has a piece which is a sparse graph or a Poisson graph, and a piece which is a complete graph with a disorder of the SK model. You multiply the piece of the SK model by square root of t, and for the sparse graph piece, what you do, you take your parameter, you take the p that you use for the Erdős-Rényi graph to be 1 minus t times gamma over n. So if you take t equal to 0, there is no contribution of the SK model, and you are in the original model of the graph. As you take t to 1, the graph disappears because the probability goes down to 0 and is being replaced in a continuous manner by the Erdős-Rényi. Okay, so what you want to do, you go over this interpolation path. Okay, so now we don't want to work directly with the maximum object, because the maximum is not a function that we can differentiate very nicely in t. So instead, what we do, we construct the partition function over balanced configuration at temperature beta, inverse temperature beta, with the interpolated Hamiltonian h of t. Take expected value, log, and divide by n. If you divide this function by beta also, and take beta going to infinity, what will happen, you will emphasize the value which is maximal here. But even before you do that, the value of the partition function is at least the value of the maximum, e to the beta times the maximum, and at most 2 to the n times e to the beta times the maximum. So for large beta, if you divide this quantity by beta, the difference between it and the hard constraint is log 2 over beta. So if you send beta to infinity, you can always minimize this error. And therefore, if you are able to study this limit when n goes to infinity and then beta goes to infinity as well, then you can study this limit indirectly by this one. So our goal is therefore to find beta that goes to infinity as gamma goes to infinity in such a way that the phi n beta at 1 and gamma divided by beta and the phi n at beta and t equal to 0 are very close to each other. We don't know how to connect phi n beta 0 and phi n beta 1, but maybe we can control the derivative. That's the interpolation technique. That's why I introduce a smooth path in order not to make the jump all at once, but make the jump slowly. So we will try to control the derivative uniformly in t and in n when normalized by beta and show that it's going to 0. So here is a basic lemma that does the work. The basic lemma says that the derivative with respect to t of this modified logarithmic, normalized logarithmic partition function, or partition function, log partition function, is going to be bounded up to a universal constant by certain things that grow with beta, but decay with gamma. So if we choose beta going to infinity, this will go to 0. If it goes to infinity slowly as a function of gamma, let's say much smaller than gamma to the 1/6, then as we send gamma to infinity, we can make this whole thing go to 0. And the important part is that all these bounds are not depending on n. So we can take the limit as n goes to infinity, and they also are not depending on t. How do we prove this lemma? We prove this lemma by Poisson and Gaussian calculus. So it's very specific to the use of the independent graph, and also somewhat specific to the Ising model, but there is a way to avoid many of these calculations and use a more robust Lindenberg type argument. What did we do? We replaced Bernoulli variables really by Gaussian variables. And if you have many Bernoulli variables, there is no reason why you couldn't replace them by Gaussian variables. You just need to make it precise and accurate. Subhabrata-san is now working on extensions of this principle. And what is the idea here, what goes on in quite large generality, is the fact that when you make the degree large, the sparse random graphs behave like some version of a disordered Gaussian model on a complete graph. And many disordered Gaussian models on the complete graph have already been solved by physicists, and many have already been proved mathematically to be the solution, to be the Parisi type solution to be correct. And there are quite a few others which have not been solved yet, but this might be a motivation to solve things which were not solved before. In particular, there are two models which immediately comes to a classical model. So if you take the max Q cut in a sparse random graph, this means just that you try to cut your graph not to 2 parts, but to Q parts. Take Q equals 3 or 4 or 5. This will boil down to an antiferromagnetic Potts model, and this will become a Potts spin glass in the disordered complete graph, for which the formula has been mathematically proven recently by Panchenko. Another example, you can take the XOR-SAT problem, which is random linear equations over 0, 1. If the number of equations is exceeding the number of variables, let's say by factor 1 plus delta, so it is impossible to satisfy them, you take a left vector, which is also chosen at random, and you make the number of variables per equation constant p. What you will arrive after some thought is a p-spin model. And the p-spin model was also solved mathematically, and the formula, the Parisi formula, is known. You can take other models of graphs which are irregular, and then you will get other models of disordered problem on irregular graphs. But the principle is that what I told you before should work. That is, the sparse random graph problems, average complexity, should be related and can be related by similar means to the problems of the corresponding disordered model. This paper is not yet written, that's therefore not yet posted, but Subhabrata is working hard, so it will be soon done. It's easier for me to say that because I have nothing to do. Okay, let me conclude now. So first of all, we saw that extremal cuts in random graphs connect to balanced Ising spins. And when the degree goes to infinity, the model with balanced Ising spins will converge to the disorder model, which has been solved by Parisi prediction. This is quite helpful and can work in many other models, as I explained, when gamma goes to infinity. This is this work in progress of Subhabrata. Some of the ideas that have been employed in this paper have also been useful for another recent work only of Andrea Montanari, by Andrea Montanari and Subhabrata Sen, but not with me, which actually uses to get suboptimal singular value decomposition methods for solving the community detection, community structure. But much more remains to be to understand, and in particular, take the original conjecture, now fix gamma, takes a regular graph, fix degree gamma greater or equal to 3. I repeat to you the conjecture, and you notice that I said nothing about it. And this is a good time to say thanks, and somebody may have solved it in the meanwhile.
Questions? Answers?
So do you expect your results to survive if you take other ensembles with average degree gamma, so some configuration model? So you've got two different ensembles with average degree gamma, and they have the same behavior. Should it be more robust than that? And should this conjecture survive? No.
This conjecture does not apply to the. This conjecture relies on regularity.
So it's not. If you take Erdős-Rényi, it's not.
No, it's not true for Erdős-Rényi, for example.
And then, but your approximate.
This is different. This is going to work.
So if you have some moment condition.
Right. If the graphs are close enough to each other, then it's going to be okay. The point is that if you send gamma to infinity, you can think of the adjacency matrix of your graph. It kind of looks closer to the one of the complete graph, and with some irregularities, and you can just remove everything except the mean and second moment, and that's kind of morally the argument behind. But this is very tantalizing because it's not really clear why at fixed degree you should have this symmetry. This I find quite counterintuitive.
That's that if you take minimum degree 3.
You need bigger than 3?
So it's not the regularity, it's the minimum degree.
This is my question. Okay.
The simulation you did was only for the regular case, right? Yeah. So the numerically overwhelming evidence for regular case, and Andrea provides moral evidence for other models.
These problems are algorithmically hard, so when you say simulations, how do we know that we solved the problem optimally?
Lenka.
So, for the simulations, how do you know that you solved the problem to optimality? Because,
Oh, well, I would not say that it's an overwhelming numerical evidence. It's an overwhelming heuristic evidence. So we basically apply this cavity method and realize that for these three problems, the resulting equations that we cannot solve are exactly the same. And then we have some numerical evidence, but that's like by just running some very good heuristics on very small instances, and this is. I would not call it overwhelming. I mean, it's a numerical evidence.
The graph looks very nice, even though you took very long to stand.
It's good evidence, but that would not make me state this conjecture is strong.
So the cavity equations that are the same for all these problems, they're not just one RSB equations,
No.
right?
No. Full RSB. That's what makes it somehow interesting from my point of view. Is that although we have no idea how to solve them in this sparse case, even numerically, it's the same equations.
Something has to be, the equations are not quite the same, right?
Yeah.
You assume that the solution is the same. You assume that the solution is symmetric, right?
Yes.
Yeah. So the equation is not the same, but if you assume that the solution is symmetric.
Yeah, and for the regular graph, then you don't see any reason why these things.
Yeah.
More questions? More numerical evidences? Heuristic evidences, moral evidences? Okay, thanks again.